So we've looked at differentiating single terms and the general rules and the way that we differentiate something. What we need to be able to do is take this from a nice simple x squared 6x to the power of 4 1 over x cubed to expand it to when we've got multiple terms and when we're differentiating slightly more complex expressions. Now, when we're doing this, there is a key rule we have to remember, and that is that we must write it as a sequence of single terms. We have to write it in that form because when we do, it's just applying it to each term individually, one after the other. So ax to the n plus bx to the n plus cx to the d plus, and then however many other terms there are after it. It has to be written in that format for us to be able to effectively do it one term after the other. I.e., if we imagine we've got it written as something like f of x plus g of x plus h of x, so different terms on their own, we just differentiate each one after the other. So f dashed of x plus g dashed of x plus h dashed of x, and we go on for as long as we need to. So a few examples of this are the best way to illustrate how to do this. So first thing we could maybe do is we could imagine getting something that's already written in the format we want. So let's imagine we had f of x equals 3x cubed minus 2x squared plus 5x. Let's imagine we had something written in that format. And I wanted to calculate the derivative. Now this is already the sum of several terms altogether as one expression. So we can straight away just do this. So we can straight away just say f dashed of x and do each term one on its own. First term, write down your coefficient times 98 derivative. So power down, reduce the power by 1. So then take away 2 is the coefficient of the next one times, and then the derivative of that part. 2 times x. So then plus 5, and it's times the derivative of x to the power of 1, which is the same as 1 times x to the 0. Well, this one here, 3 times 3 and then it's x squared, gives you 9x squared. Minus 2 times 2x gives you minus 4x. And this last one is 5 times 1x to the 0. Well, anything to the power of 0, remember that from Arrhenius laws, is 1. So it's 5 times 1, which is 5. So there we go. We've got our final answer. Anything like that where it's an x and it goes to x to the 0, it's just going to be 1. It's going to be a constant left over. It's straightforward when we've got, and that doesn't matter how many terms we've got. We could have as many as we want. So I could have 6x to the power of 4 plus 2x cubed minus x squared plus x minus 18. I could have something like that. 5 terms. They're all written one after the other. I've got them in the form I want. I can just do the derivative and go through each term one at a time. First term, 6 times, bring the power down 4, reduce the power by 1. Second term is plus 2 times, then the derivative of this. 3x squared, bring the power down, reduce by 1. So then take away 1 times 2x to the power of 1. That's plus x to the power of 0, because it's 1 down, 10x to the power of 0. And then it's minus 18. Now there's nothing here that depends on x. There's no x part of that term. When you take the derivative of something that has no dependence on it, it just becomes 0. So this term here doesn't even get put down because it becomes 0. So what that means is I can go through each of the terms on their own. So I'd get 24x cubed plus 6x squared minus 2x plus 1. Again, remember x to the 0 is just 1, so it's just a 1 left there on its own. We're able to go along and do every single term all on its own, one at a time. Now, we have to remember that this is how it has to be written. It has to be written as a sum of several terms like this, all in this same format, your ax to the n. Doesn't matter about the power of n. Remember, we've covered looking at that as a fraction, we've covered looking at that as a negative number, as a positive number. It just has to be written in this format. Let's imagine I give you the expression y equals x minus 2, x plus 3. Now the first thing to note about this, it's not in the format we want. It's not written one term after the other. in the format we want. So we now have to make sure we do that. Well, think back to double brackets like this when we did it at National 5, multiplying them out using FOIL. So first, outer, inner, last. So first gives you x times x, outer plus x times 3, inner minus 2 times x, and then last is minus 2 times 3. So that gives me x squared, 3x minus 2x gives me a plus x, and then minus 6 there. So now I have it written in the format I want. It's written the way we need it. We can do the derivative. So I can calculate dy by dx now. And it's just a case of going through it term by term. X squared, bring the power down, reduce it by 1, so I get 2x. This one here is just a plus an x, so that becomes plus x to the 0. And this is a constant. There's nothing depending on x here. It just vanishes. So we then end up with 2x plus, remember we don't want to leave x to the 0 here, so we just leave it as a 1. So we get 2x plus 1 as our derivative. First step is to make sure it's in that format, and it doesn't matter about the format of the original function. We have to make sure it's written like this every single time. Let's up the ante a bit then. Let's see if I tell you f of x equals x over 5 plus 1 over x squared. Let's imagine I've got something written like that. Now, this is separate terms, yeah, but they're not written in the correct format. They're not written as x to the n. This one pretty much is, which is fine. This one isn't. It's 1 over x squared. Think back to when we did the Indus laws in the previous video. We can write this using a negative power. So that'd be the same as saying 1/5 times x for the first term plus x to the power of negative 2. Remember, we bring it up, power becomes negative. Now I've got it written like this. Now I've got every single term of that form. Now I can calculate the derivative. It has to be done every time. Working each of them through, write the coefficients, so 1/5 times x to the 0, bring the power down, you've got minus 2 times x to the negative 3. And then it's just a case of simplifying it. X to the 0 is 1, so I just simply get a 1/5 minus 2 times x to the negative 3, 2x to the negative 3 there. That's me got my derivative now. That's me got it ready to go. I could also then take this a step further and rewrite this as positive indices. So I could have that as a 5th takeaway. Well, this one here, think back to when we had a over x to the n. We were able to write that as ax to the negative n. So we were able to go this way, but we're also able to come back that way. So this here is written as ax to the negative n, negative 2x to the negative 3. I can rewrite that as negative 2 over x cubed. I can rewrite it all with positive indices and leave it in that format. This is very effective and something that does come into play quite a lot when we're working with it. So we have to bear that in mind. And this applies regardless of the complexity. So I'm going to look at one more example, but I'm going to really up the ante this time. Imagine I said to you, f of x equals x cubed plus 2x squared minus 6x over the square root of x. So imagine I told you something like that. Now that certainly isn't in the way that we want it, but we have to get it in that format that we're after before we can do anything. First thing, write all your powers as numbers. So these are all powers, great. Square root of x, we know this can be written as x cubed plus 2x squared minus 6x over x to the half. What I can then do is separate this into 3 separate fractions, all with the same denominator of x to the half. So I can write it as x cubed over x to the half plus 2x squared over x to the half minus 6x over x to the half. So I've got 3 separate fractions. So now what I can do is simplify these using more of our Indus laws. Think back to when we did this. If I had x to the a over x to the b, I could simplify it by doing x to the a minus b. And I can do the same for each of these. So x cubed over x to the half, that gives me x to the power of 5 over 2. simply subtract 3, take away a half. Second one, the coefficient stays the same, so it's 2. It's x to the half over x to the 2 over x to the half. Gives me x to the 3 over 2. Minus 6, again, the coefficient stays the same. It's then x divided by x to the half. That gives me x to the half. Now, they're all fraction powers, yeah, but it's the format we want. Ax to the n plus bx to the m plus cx to the d plus blah, 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 blah. It's term after term after term. It's the right format for f of x. This is how I want it written before I go on to do my derivative f dashed of x. And then we just do term by term. And it's the same rule. Bring the power down, 5 over 2x, reduce it by 1 to the 3 over 2. Second one here, coefficient in front, bring the power down, 3 over 2x, reduce the power by 1 to the half. Then it's minus 6 times, bring the power down, x, reduce the power by 1. And then you just simplify it. So first term's fine, 5 over 2x to the 3 over 2. Second term, 2 times 1.5 plus 3 x to the half, and then the last one, minus 6 times a half, minus 3x to the negative a half. I've managed to get it, take the derivative and get it written in that format. And again, we can use the powers and our rules to write this so that we don't have fractional indices or negative indices. So I could write it as 5 over 2 times the square root of x cubed plus 3 times the square root of x minus 3 over square root of x, using the index laws we talked about previously. When we're working through derivatives, it's vital that we remember this. It's vital that we remember step 1, get it written in that format where it's the sum of several single individual terms written like that. And then once we've done that, we can take the derivative of each one after the other, and then we can take it from there.